Hi there, we're going to review some of the concepts in lessons 1 and 2 of the radicals unit, unit 5. So let's take a look. First, we're going to look at numerical, so irrational numbers and simplifying them. So in the first one, this is basically math 10. So simplifying root 72. Things that you should remember, should try to memorize your perfect squares. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, at least up to 100. If you can get memorize 11 squared is 121 and 12 squared is 144, that's helpful too. Cubed roots, really only going up to about 5 cubed. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. If you can remember the rest, that's great, but these are the most common. And I mean, you do have your calculator that you can check certain values if you need to. So I always suggest that you're looking at the radicand, the number underneath the radical, and looking for the largest perfect square. So you might think, oh, 4 goes into this, which it does, but it's not the largest. If you do 4 to start, then you're going to have to simplify twice. So the biggest one, basically, 81's too big, 64 doesn't go in. So start with a number, highest perfect square, less than 72. So 64 doesn't go into 72, 49 doesn't, but 36 does. So then I rewrite this as 36 times 2, and then the perfect square is what we take the root of. So that's root of 36 is 6, and the 2 stays underneath. So my kind of analogy is the radical sign is like your house, the roof of your house. And this is the perfect child because it's a perfect square, and the perfect child gets to go out on the weekend. And what do they dress up as? 6. Okay, so you have to take the root of 36. They have to change before they can go out on the weekend. And then the 2, the non-perfect number, has to stay home. Okay, and then if you want to check, your calculator cannot simplify radicals, but you can enter your original value, root 72, get the decimal form, enter what you think is your simplified, 6 root 2, and make sure those are exactly the same. If they're not, so a common mistake is people will go 2 root 6. They'll get those numbers mixed up. It's not the same. So you know that you've done something wrong if you went 2 root 6. Okay. Then multiplying radicals. So you have to, if they're mixed radicals, you have to multiply the coefficients and multiply the radicands. You can't mix and match. So that's going to be 6 root 150. And then you have to simplify 150. So that's going to be 6 150. So again, this goes up to 121. Obviously, none of these will go into it evenly. So by evenly, I mean a natural number factor. So basically, you want to go down to, and the 0 is a kind of a giveaway. 100 doesn't go in. It's got to have a 5 then. So 25, does 25 go in? It does. 25 times 6, and then 25 is the perfect square. So that's going to be 6 times, root of 25 is 5, root 6, and then just multiply those. That's going to be 30 root 6. Now, you don't have to take all of these steps. You can really go from 6 root 150 to 30 root 6 if you want. I'm not going to be marking part marks. Okay, I'm just going to see if I can move my screen a little bit to get in this question. So here, This is distributive property. So if you remember back to polynomials, you may have used the word FOIL to help you expand. So that'll be first together. So that's going to be root 12. Then outside together, it's going to be minus root 36. Inside together is going to be plus 2 root 6. And last terms together will be minus 2 root 18. So remember, when you're multiplying, just like back here, only the coefficients together and only the radicands together. So that's why in this one, it's going to be 2 times 1 is 2, 3 times 2 is 6 in the radicand. Then simplify if you can. So 12 is 4 times 3. Again, you don't have to show this step, but I'm showing it here. Root 36, well, 36 is a perfect square, so don't show any work, it's just 6. Keep the same sign. Then plus 2, root 6 can't be simplified. And then minus 2, root 18. Well, 18 is 9 times 2. So 4 is the perfect square, so that's going to be 2 root 3 minus 6 plus 2 root 6. 9's a perfect square, so that's going to be minus, just going to erase this little line here, 2 times 3 root 2, right? Root of 9 is 3. So now, if you take a look, I'll simplify that in my last step. Look at the radicands. If there's any like radicands, you can collect them. There aren't any. So then you can put them in whatever order you want. You might want to put the largest radicand first, then 2 root 3, then minus 6 root 2, and then the integer at the end. It really doesn't matter. Okay, so that's multiplying binomial radicals. Then dividing. So when you're dividing, take a look. Maybe the radical in the denominator can divide into the radical in the numerator. So if you take a look here, this is the same as, because they're both square roots, we can show it as one complete square root of 12 over 3, which simplifies to 4. Root of 4 is 2. So always check, can the 3 go into the 12? Only the radicals together, only the coefficients. Just like multiplying, only the radicals together, the radicands, and only the coefficients. Next one, 5 doesn't go into 3 here. So we have to do what we call rationalize the denominator. So here, when we rationalize, we need to multiply through by the radical that's in the denominator, top and bottom. Okay, just like any fraction, as long as you multiply the numerator and the denominator by the same value, you haven't changed the fraction. So just look at this. We don't care about the 2. It's good. It's rationalized. We're trying to make this denominator, which is irrational, into a rational number. So multiplying top and bottom by root 5. So then I'll go back to my here. I'm just multiplying the top, which is 5 root 15. And then here in the bottom, that's going to be 2 root 25. Okay, you don't have to show this step. The whole point of doing this is root 25 is 5. So this is really going to be 5 root 15 over 10, right? Because this is equal to 5. Now you want to see if you can simplify the coefficients, right? So this is a rational number. This is rational. So we can divide 5 into that once, into this twice. So our final answer, simplified answer, is root 15 over 2. This type of question is probably a good idea to check. Again, your calculator can't do it for you, but you can put in the original. Some of you may have the option of doing fractions, so I'll do it both ways. So alpha y equals, and if you choose n over d, that's going to give you a fraction. So then you can go 5 root 3 over 2 root 5 and gives you the decimal form. Then in your answer, you have root 15, then arrow down to 2, not in the radical, enter, and it's the same. So you know that you've done the correct work. If you don't have a calculator that allows you to do fractions like this, then just use brackets. So I'm going to go bracket 5 root 3, cursor out of the bracket, close the bracket, and then divide bracket 2 root 5, cursor out of the bracket, close it, out of the radical, close the bracket, and you get the same thing. So just use brackets and division symbol. Okay, so that is rationalizing with a single term. Now rationalizing with two terms, that's where we have to multiply through by the conjugate. So what's the conjugate? If you remember back to Math 10C and polynomials, conjugate is the same terms but opposite signs. So whether it's algebraic or radicals. So here, same terms, opposite sign. And we have to do the same in the numerator. Again, because multiplying a fraction, you have to do the same to the numerator and denominator in order to keep them being equal. So now when I expand out here, my hint is if it's just a single term in the numerator, then keep it in factored form just because you might be able to simplify and you don't want to have to factor again. So I'm going to keep it like that. But then here, when you're multiplying by conjugates, what happens is, remember with polynomials, if you have x minus 2 times x plus 2, it gives you a difference of squares, x squared minus 4. The first term squared minus the second term squared. So that's what's going to happen here. You get root 25, which is 5, the first term squared, minus root 15 plus root 15, which goes away, and then minus root 9, which is 3. Okay, so that's your perfect square, and that's your perfect square. So now you can, again, I'm not going to expand out because I notice here 5 minus 3 is going to give me 2, which goes into 4. Oops, sorry, there's 2. So then I'm going to divide 2 into itself and into this twice. Oh gosh, sorry, I'm not doing well with my tablet here. These twice, and so then I'm left with 2 root 5 minus root times root 5 minus root 3. Now I'll expand out. Okay, and if I had expanded this, then I would have to have factored the 4 and then divided out. So it just saves you a step. Okay, so that's rationalizing the denominator. Right now, the denominator is 1, so we don't even show it. And that's a rational number. Okay, next one. Again, need to rationalize the denominator. Taking a look at this, now there is a coefficient there, so we do not leave it out in this case. Back in with one term in the denominator, we didn't multiply by 2 root 5. In this case, we have to multiply through by the conjugate, so that means the conjugate of the whole denominator. So that's 2 root 3 plus root 5, right? Opposite sign. So this is 2 root 3 plus root 5. Okay, and then again, I'm going to think about what I'm going to do in my next step, because this has a radical here. So you could leave it out to start, but maybe when we multiply by root 2, it might have something that can simplify, although I can tell that it won't. I'm going to leave it out to start, maybe my denominator will have simplified to a 7. I'm not sure, but I'll expand that in a few minutes. So then I'm expanding this out. So the first term squared, so 2 root 3 times 2 root 3 is 4 root 9, which is 4 times 3, which is 12. So 2 root 3 times 2 root 3. That's 4 root 9. 4 times 3 is 12. Then the outside and inside add to 0, and then minus root 25, which is minus 5. Okay, and so it does turn out to be something that I can simplify. I can see here that this is going to be 7. So 7 root 2, 2 root 3 plus root 5 over 7, and then those 7s divide out. Okay, I can divide that out because it's a factor. It's not in a single term. Okay, and then, so now I'm going to expand out the root 2. So that's going to be 2 root 6 plus root 10. Okay, and that's simplified form. And again, you can enter that in your calculator to check. Neither of these can simplify. Okay, so that's all the operations with irrational numbers. Now we're going to look at simplifying radicals that have variables. So same kind of thing. There might be some numbers in there that we have to simplify, just like normal. And then there's variables. So we have to think, any root like this that doesn't have a number is a square root. So this is back to Math 10C. Okay, square roots, if it's a cubed root. But looking at the variables, that's something a little bit different, but really shouldn't be, it almost gives it away. So this is x squared, so that means it is a perfect square. So when I do ones with variables in them, I start with the 20, the number, and write it out as a product where one of them's the largest perfect square. Then I look at the variables. Is this a perfect square? It is. If that exponent is an even number, it's a perfect square. This one's not. It's a 5. So then I have to think about how can I express y to the 5th as a product of exponents on y that multiply to y to the 5th, okay, where one of them's the biggest perfect square. So perfect squares are even exponents. So really, you look at the next lower even number. So that's 1 less than 5. And then this will be a 1. So now when I show this, it'll be y to the 4th times y. Then my perfect squares are the 4, the x squared, and the y to the 4th. So they get to go out on the weekend. So root of 4 is 2. Square root of x squared is x. Square root of y to the 4th is y squared. Okay, what stays home on the weekend? 5y. Okay, so that's how you simplify radicals with variables. So we'll do another one. This one has a 4 out front, so we'll just leave that. Perfect square that's a factor of 27, 9, so that's 9 times 3. Then is this an even number? It is, so that's x to the 16. This is not, so next lower even number is y to the 8 times y. Okay, so perfect squares, that's 9, x to the 16, y to the 8, so they get to go out on the weekend. So that's going to be 4 times root of 9 is 3. Square root of x to the 16 is not x to the 4th. You're not square rooting the exponent. You are square rooting x to the 16. So it's going to be half of 16, if you remember back to Math 10C. So that's going to be x to the 8, because, and you can check it. X to the 8 squared is x to the 16, your power loss. Square root of y to the 8th will be y to the 4th. Okay, and what stays underneath? 3y. So now I'll just write this all together. 12 x to the 8, y to the 4th, root 3y. Okay, and then cubed roots. Same process, except for cubes. So we're looking for perfect cubes. Perfect cubes, if you remember back to your perfect cubes I put up here, 64 goes into 128. So that's going to be 64 times 2. Is this exponent a multiple of 3? Square roots, we looked for multiples of 2. Is this a multiple of 3? It is. So that's x to the 6. Is this a multiple of 3? No. So what's the next lower multiple of 3? Would be y cubed. So that's what I put in. Now, this is a perfect cube. This is a perfect cube. This is a perfect cube. So the perfect cubes go out on the weekend. It's going to be 4. Cubed root of x to the 6. Well, remember that is basically how many x cubes are in there. Sorry, how many squares. So when you square something, you have to get x to the 6. So that's x cubed, right? So really you're dividing this exponent by 3 to get the new exponent. So that's x cubed, dividing this exponent by 3 to get y, and then cubed root, don't forget the little 3, of 2y. Okay. Next one here, and something just to remember in terms of restrictions, we haven't talked about that, but it does in the lessons. This is only defined here if x could be negative here, because when you square it, it's positive. Y would have to be positive, okay, when it's to the exponent 5. Because a negative would leave a negative in there. So there are restrictions. This would have to, could be both positive or negative. This would have to be positive. Here, for cubed root, it doesn't matter. X could be and y could be anything because cubed, you can take the cubed root of a negative. This one, 3x, we leave out. Cubed root, so cubed root of 24 is 8. So 8 times 3 is 24. X squared, not a perfect cube, and there's nothing that we can do. So we're just going to leave that. Nothing lower than that that's a perfect cube. And then y to the 9th, that is a perfect cube. So now I'm going to circle my perfect cubes. Then I'll have 3x, and then multiplied, cube root of 8 is 2. Cubed root of y to the 9th is y cubed. Cubed root of 3x squared. They don't get to go out on the weekend. And then simplify your coefficients here. So that's going to be 6xy cubed, cubed root of 3x squared. Okay, and then last one is adding radicals with variable radicands. Just like numerical ones, they have to be exactly the same in order to be able to add them. And then as well, if there's variables outside, you need to have that variable outside as well. So for this, there is nothing I can do to simplify the first one. There's no square root of 3 or x. Second one, I can. 27 is 9 times 3. X cubed I can show as x squared times x. That's a perfect square. That's a perfect square. So that's going to be 3x outside and 3x inside. They're worth different because this is a radical, right? So that's a radicand. This is coefficient here. Now you need to check, is the radicand exactly the same? It is. And then if there's a variable outside, is this exactly the same? It is. If that had an exponent 2 on it, you couldn't add these together. But it is, so now that means We add them just like variables, so 4 times this plus 3 times this is 7. 7x root 3x. Okay, so that is a quick review of lessons 1 and 2. Hopefully that helped you.